The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released.
Alright, I'm glad that you like the video. Over here we are trying another mode of presentation so that we get a clear idea of whatever happened. I've shown you a video, showing you a graphical representation. I'm going to show you the real life demo. I'll pick a boy later. Okay, so what happened is that because of the presence of the halogen, you generate the delta positive and the delta negative situation. And that delta positive attracts the nucleophile. Nucleophile that has a lone pair, or nucleophile has a lone pair and a negative charge. When this happens, you need to see this structure in a tetrahedral manner. When I have the halogen on the other side, I cannot be attacking from exactly the same side. So the nucleophile will come from the back, and they will go through this situation when we call this a pentavalent transition state. Really, because penta means 5. If you look at the carbon here, it's kind of linked to 5 things in the transition state in a very short time, actually. So in the sense that we move on like this, you look at the representation that I'm having, I actually have an arrow going through the square bracket. Because this is the transition state, it's within one step, it happened. And then I have the product being formed, make sure that I have eliminated my X minus, the halide ion there. Things to take note, transition state has a negative charge overall because my nucleophile was negative charge. If the nucleophile that I use does not carry the negative charge, then my transition state is not negatively charged. You understand what I'm saying here? Okay? So in this particular transition state is what my analogy always says in the two timing situation, where the new boyfriend is already in the picture and the old boyfriend has not completely left. It's an awkward situation and they will quickly settle the problem. Is that okay? Spatially, we also need to recognize that it was a tetrahedral, where the 3 bonds are pointed in this direction and the halide is in this direction. After your nucleophile is being attached and the halide has left, your molecule needs to optimize again. That means the bond pair will need to repel, and so that they will flip over to the other side. That's why we will call it an inversion of stereochemistry, or inversion of configuration. So the transition state is shown in the square bracket. If X were to be bonded to a chiral carbon, which means if your starting material has a chiral carbon center, then the stereochemistry at the carbon is actually inverted. I think everyone is okay with the two timing part. You're also okay learning the drawing. The only problem that we might have at this point probably is the flipping, also called the inversion of stereochemistry. Going through the energy profile diagram, which you had an animated version earlier, your transition state actually fits right on top of the peak. Now when we have taught you earlier, when you have a carbocation intermediate or whatever that you have learned that has the term intermediate, intermediate is a product of the first step and the reactant for the second step, which means intermediate will happen or appear here right before you go for the second step. But transition states are the ones that is right on top of the peak. That it is only there temporarily and is gone. One very important thing that I need you to take note of will be, because the slow step, as our mechanism has shown, involve both the alkyl halide and the nucleophile, then when I give you the rate equation, it will look like this. This equation will hint or signify to you that it has undergone a SN2 reaction. So I'm going to show you in a physical manner how the inversion actually happens. We tried it. You see the 3R group that is being attached. Now you need to work with me here. The halogen is something that I don't have. It's sticking in this position and it's right there. So can you visualize the tetrahedral first? Can you visualize the tetrahedral? The halogen is right at the other end. I have 1R group, 2R group, and 3R groups in a tetrahedral manner. Okay? I am acting like the nucleophile. So I'm attacking from the back. And when the halogen leaves, that's what we meant when we say there is an inversion. Because the new product involves the nucleophile and the 3R groups. Thank you very much for your encouragement. No, I'm not going to do it again. I'm sure you got the idea. Okay, so what are the partial charges of nucleophile and halogen in the transition state? Let's think about this here. When the nucleophile is approaching, now the dotted line here really represents that it is going to form a bond. The bond is not formed yet, but it's in the process of doing so. And the dotted line on the other end between the C and the X signifies that that bond that they used to have is breaking. So what do you think are the partial charges on the nucleophile and halogen in the transition state? Talk to the friend next to you. Looking at just the transition state, the nucleophile was carrying a negative charge. He had a negative charge, but in order to do the attack, okay, I will stand on this side to align because you picture me as the nucleophile already, right? So I put the lone pair of electrons that I have, I donated in order to initiate the forming of that particular bond. In a way, I will be less negative than what I started out to be. Can you appreciate that? So I started out with a formal negative charge, but when I start doing that, in the process of doing so, I'm losing some of my negative. And so I will be slightly negative, no longer a formal negative. Can you appreciate that? Where on the other end, I was supposed to have a bond, if I'm the X, the halogen, supposed to have a formal bond with the carbon, but I'm getting ready to leave. And since you're going to kick me out, I'm going to grab everything and go, right? So I'm pulling the electron closer to myself, and I'm ready to leave as an X minus. So at this stage, I am also being delta negative. Can we appreciate that? Okay, then the energy profile diagram is shown below. We have done this already just now, nothing new. Now, SN2 mechanism, as what we have talked about, I keep using the term backside attack. I need to attack from the back because, I need to leave halfway for the halide to leave. Let's be nice and not block the halide, right? So as a result, there will be a concern about whether or not the nucleophile can approach the carbon. Why does it have to do with primary, secondary, and tertiary? We must appreciate the nature of the nucleophile. I am electron rich. I have a low pair, or I have a negative charge. When I have substituent group, alkyl group per se, they essentially are electron clouds. Agree? Negative doesn't get together with negative. So if you have a lot of groups or big groups around the carbon, it is very difficult for the nucleophile to approach. Do you understand where I'm going from? Because negative repel negative and it's blocking. The nucleophile cannot approach the carbon to establish the new bond. As a result, SN2 mechanism will be favored by primary alkyl halides. Primary alkyl halides prefer to go through whatever that we have learned, SN2 mechanism. It is easy to perform a backside attack on a primary alkyl halide. It is possible for secondary, but it will be difficult. It will be difficult for it to happen on a tertiary alkyl halide. Pictorially, if you missed me just now, let's look at it here. If I have 3 branches that all have a rather big electron cloud, it will be difficult for a negative OH minus, for example, to approach the carbon. So primary prefers SN2, but tertiary don't really want to go through SN2 mechanism. Examples that is both printed on your notes in quite easy to understand. Okay, if I start with an alkyl halide and I have Cn minus coming through, undergo a SN2 mechanism, they will attack directly. Now some of you read my notes partially and ask me, then how come the electron go from the bond to the VR? Because the VR is delta negative, what? How come it will still go there? This flow of electron here is triggered because the nucleophile attack your carbon. Carbon can only have 4 bonds. The moment your nucleophile attack carbon, it is in a situation of 5 bonds. So it will get rid of 1. And so that's why you trigger the second arrow. Is that okay? Then this arrow through your square bracket giving me the transition state. I have a pentavalent transition state, and I get the final product here. But the flip of the umbrella, the configuration is inverted. Not forgetting my Br minus. The ex-boyfriend that got kicked out needs to be there to balance my equation. Please take note, by September or October, this will become a common mistake. Please take note that your Cn minus actually has a triple bond. The lone pair is on the carbon. That's why the new bond to be established is with the carbon and not the nitrogen. Should have learned this very long ago, right? Okay? If you have the time, you should also try drawing out the dot and cross diagram, make sure you know what you're doing. Reaction with alcoholic ammonia. Again, we start with the same material, delta plus and delta minus will always be my marking point. Now because I'm working with ammonia, this is the case where the nucleophile does not contain a negative charge that I was trying to tell you. Attack from the lone pair to the carbon. Transition state. It's exactly the same pattern, if you can see it. Take note, because my nucleophile does not have a negative charge, my transition state also does not have a negative charge. Then I will get the product out of it. Now, you notice that it is a situation where the nitrogen actually carries a positive charge. Why? Because in this structure, nitrogen has 1, 2, 3, 4 bonds. But they can easily fix the problem by getting rid of the H+. That is why you will have this being formed. Also notice that my Br minus has now become the HBr because the H+ is being kicked out and pick up the Br minus. You cannot put HBr too early because the H+ needs to come out. This is also the one that we spent some time on Monday to talk about, where the lone pair is still on the nitrogen. And the nitrogen still has the capability to attack because the lone pair is still around. You recall? Until you get the complementary sort. That being said, that's the end of SN2. SN2 is when your nucleophile attack the carbon directly. There is a pentavalent transition state. They were 2 timing momentarily, very, very quick. In the SN1 mechanism, those are the nicer girls who get rid of the ex-boyfriend first before they accept the new coming nucleophile. SN1 mechanism involves 2 steps and the formation of a carbocation intermediate. Look at it here. This is the one. To form a carbocation, we need to recall. This is the concept that you learned since alkenes chapter. Carbocation is more stabilized if the carbon is more substituted. That is what you learned when you first learned your Markovnikov rule. And that idea doesn't go away. So over here, if I were to form a carbocation just like this, the carbon must be comfortable bearing with the positive charge. The only way it can be comfortable bearing with the positive charge is that it has a lot of substituting room. So in this case, the CX bond will actually break slowly, but it will break to form a carbocation. Now I need everyone to pay attention on the screen. This carbocation is essentially a trigonal planar. Is there any more? I need to sacrifice one more. I don't do nonsense with those. And I promised Nelson not him today. Not today. I need a cheerful boy. You look cheerful enough when you're looking at me.
Brian.
Stand up.
Brian.
No, actually I'm looking at the boy that was doing that. Stand up please. No, not the one with specs. Stand up please. Are you in a stable manner? You're secure, right? You're not going to roll down the slope, right? Okay. Now, how does your carbocation actually look like? Could you please raise up your two hands in a Y shape? Why? I'm not going to demo to you. Yeah, raise up your two hands in a Y shape. Yeah! Alright, the left hand and the right hand both represents our group, and the bottom of the feet is the third our group over here. You see the orbital that I draw at the side? I'm just trying to show you that you can attack him right now from chest front or from the back. No, Nelson, no. So, can you rotate? You can see it now, he's in a trigonal planar situation where you can attack both from the front or at the back, and that will result in two different compounds being formed in terms of enantiomers. Thank you very much. So this is what I was trying to tell you. This intermediate carbocation demonstrated by the boy there showed you that you can actually attack from the left-hand side or the right-hand side, because I'm showing you a paper, but showing him as a person that you can see his front and the back. So you have options here. Then I'm going to ask you, which one has a higher probability? What do you think? It was flat. It's just a trigonal planar. What are the probability of him getting hit in front and at the back? Excluding his face being inviting. So front is my favorite, but how? Will it be a difference if you think of in terms of molecule? No, right? So it's 50% chance. If you can appreciate that, I think his sacrifice today is worth it. Alright, so the carbocation is sp2 hybridized with a vacant p orbital. Take note, everyone listen up. In your drawing of the mechanism, I do not want to see the orbitals. The loops there is to tell you that you can attack from both sides. But in your mechanism, you don't need to show me that. Okay, so when you try to attack from the right, you will get this particular structure. Now, why would I suddenly draw it like this? Because it will optimize. The bond pair will repel the bond pair. They will optimize in the form of tetrahedral. And when you attack from the other side, you actually get the other product being formed. So in your words just now, you are telling me that they will be of equal probability. One of them is retention, the other one is inversion. And if you're starting with a chiral center, then the two of them would have been mirror images. What do you call this? When you have 50-50 of the two mirror images, that mixture is called racemic mixture. You have learned this back in Sec 4. You didn't have a Sec 4? I'm going to pull out the list of tutors that I taught you when you were back in Sec 4. Okay. Now when you have equal amounts of the main form in the same mixture, we call that racemic mixture. And racemic mixture does not exhibit optical activities. You see, right from the beginning of the chapter, I was trying to tell you that, hey, you need to know your primary, secondary, and tertiary, because with that information, you can decide which mechanism to draw. Now I'm giving you another piece of information. If they tell you that you start with one of the enantiomers, and then you end up with the optical activity inverted configuration, then it must have been SN2. If they tell you that you start with one that is optically active, after the reaction it is no longer optically active, meaning it is a racemic mixture, they are telling you that you went through with a SN1 mechanism. I think I have bulk of the physics students here, so I'm just going to go fast. Optical activity is something that you should get in touch when you do secondary physics. I know not everyone did it, right? So if you think of the machine that I actually use, I have a small cuvette and I put the solution inside. Inside the machine there will be a light source, not necessarily the light bulb. There will be a filter so that eventually the light that is hitting my sample is a plane polarized light. Then we will get to measure and analyze whether the sample has an impact on the plane polarized light. The understanding must be there when they are mirror images. The degree is not fixed, but say for example, it is 12.5. This guy will be able to rotate my plane polarized light by positive 12.5, whereas the other will rotate it negative 12.5. When I have a mixture of the two of them, I will have no rotation. Okay? That being said, the energy profile diagram now for your SN1 mechanism, because it involves two steps, that's why you have the two humps. Activation energy of step 1 is really large, and that is also the slow step. You will have the intermediate at the end of step 1. In SN2 reaction, we have the transition state highlighted for you. But this one, the carbocation ion, is an intermediate. It's produced at the end of step 1. And then when the intermediate carbocation ion undergoes step 2, the activation energy for step 2 looks like this. Can you see the difference here? Step 2 is also the fast step, it's not the rate determining step. And when I go through with it, I get my final product. Now, because when we draw an energy profile diagram, we want to make sure everything is balanced. So despite the fact that the nucleophile is not in use for step 1, I leave it there because I need the nucleophile for step 2. So my nucleophile cannot just pop up in the middle of nowhere. The diagram does not make sense. Step 1 is the slow step. It has high activation energy required because it needs to break that particular bond. Just like when there's no bond formation, it's just breaking off that one bond. Now those of you who are faster and done with copying, can you suggest what is the structure at point X and point Y then? Just a quick sketch. What do you think is happening at the peak X and what is the chemical species at the peak Y? Sketch it out. You can use a pencil, things that you can erase later. Those of you who are slightly lost, you can follow my voice. Those of you who know what you're doing, quickly draw. I'm going to show you the answer. In slow step 1, I am just doing one thing and one thing only, right? I'm only breaking the CX bond. Agree? So at the peak over there, I should be in the process of breaking the CX bond. To show me that you are in the process of breaking the bond, you will use dotted line. Because the X is leaving as X minus. So with this as an example of reference, can you quickly draft out the answer you will give me for Y? Once you're done, can you look up at me so I will show you the answer and we move on. I'm asking you to try Y first before I show you the answer. Okay, can tell quite a number of you are done. This is what I'm looking for. It's going to be formed, but not yet. The reason why I do this with you is now that you have done all the X and Y, you have a perfect energy profile diagram that you should not be confused between transition state versus intermediate. They are very different. Position on the energy profile diagram should help you to remember that as well. So because for your SN1 reaction, the rates determining step only involve the alkyl halide. The reaction is a first order reaction with respect to just alkyl halide. To sum it all, it means that if no hint is given, you look at whether it's primary, secondary and tertiary, you can decide for primary and tertiary. In the events that they give you secondary, and they have never said anything, then both answers need to be marked correct, but they won't do that. So they will give you a second tier of hint. The hint code comes in two shapes so far. Number one, they talk about optical activity of the product. Number two, they can give you the rate equation. So that piece of information will help you in deciding which mechanism to draw. SN1 mechanism favored by tertiary alkyl halide, as we have discussed about, because of the stability of carbocation intermediate. The more substituent you have, the more stable the carbocation, and therefore they will prefer the SN1 mechanism more. Please refer to alkenes for details if you're still struggling with stability of carbocation. So how does it look like when you draw it out? Now reminder again, do not draw the loop for us when you are submitting your work. Step 1 is a slow step. The CBr bond will break, you will get a carbocation. You can get the new profile and tag right now. Like this. Of course you can get the other optical isomer. If you have the cyanide ion, look at it here. The first marking point that I will have, of course, is your delta positive and delta negative. The curly arrow, where it accurately goes from the bond to the Br atom. The word slow on the arrow is also important. The correct structure of carbocation in the side product of Br minus. Then the nucleophilic attack, fast step, and giving me the product. Take note once again, the bond is a CC bond. You form a CC bond and not a CN bond. So there's a possibility of retention of configuration, but we can also attack from the other side where we have an inversion of configuration. Alright, compare and contrast your SN1 and SN2 before we have the let's draw it together thing. For your SN2, there is one step in your entire mechanism, whereas your SN1 has two steps. Your SN2 is favored by primary alkyl halide, your SN1 favored by tertiary alkyl halide. SN1 only has one product, whereas SN2 only have one product, SN1 only have two, because you have the front attack and the back attack. Then SN2 you can have an inversion of configuration, SN1 you will have both, and that's why you end up with a racemic mixture. Make sure you highlight to yourself, racemic mixture means that it doesn't have any optical activity, does not rotate your plane polarized light anymore. So how should it look like? If we were to be doing an SN2, find a space on your lecture notes or pick out a piece of paper. I will have this, and it is your common habit to start drawing the organic compound first, and then you will be stuck in the situation where you have the nuclear file. And then you suddenly remember that your teacher said must backside and back. So I will end up many a time with arrows like this. Which I don't hate you for it, but you can do better. Because at least you give it in the sense that it comes from the lone pair. You know, you have a lot of space and your font size can change. So you can actually squeeze it here. Oops. And then you can type from here. I would assume your paper and pen one will be much nicer than mine. The stylus is not really that easy for me.
Why would the bond do it? The bond do it.
Okay, straight arrow with the square bracket. Close the bracket with the negative charge because my new profile has a negative charge. You understand the square bracket is like zooming into the arrow. Okay? And the pentavalent that I need will look like this. Prime, prime, H. Okay? Ugly, but it proves a point, right? You know what I'm doing? I really hope everyone can like draw together since I'm spending the time to draw it together with you. Do you have a pen? Young lady, I'm really looking at you. Can you please draw together, act like you're drawing together with me? Alright, so as a result, we will get okay? Oh, I have missed out one arrow. Which one is it? Okay? Can do. If we were to do SN1, we are looking at 2 steps, right? So we'll be starting with this. Carbon cation. So we're saying that the new profile can attack from this side. Do you need to show me both? No. You need to show me two products where you can give me one of the nucleophilic. That means you show me orange or green. But I understand that you get two products out of it. So I will get okay? Where should be orange here? Do I need to redo it in orange? Okay? Are you confused? Do you want to see the carbocat ion again? We have a dedicated carbocat ion there that can help you to understand why you can access from the front and at the back. So SN1 mechanism is favored by tertiary alkyl halides because it forms the most stable carbocat ion really, and your primary alpha halide produces the least stable carbocat ion, so it prefers to undergo your SN2. We have talked about this earlier for your SN2. All that you have left specifically push you for either primary, if not tertiary alkyl halide. So if the question gives you a secondary alkyl halide, then the problem comes. Because both SN2 and SN1 are possible and will occur. Then they will need to give you a hint. What are the two possible hints that we know of? Number one, the rate equation. The moment they throw the rate equation and structure to you, you will know whether it's SN1 or SN2. Or they can tell you about optical activity. But it has a restriction. You must have started with something that has a chiral carbon, and they tell you that it's a pure sample of one of the enantiomers. Now towards 2 months later, there will be students that is slightly confused and try arguing with me and say that, hey, the question say that I end up with a racemic mixture. It means that for my enantiomer to go through the reaction, some of them have the inversion one, so it's possible to get SN2. I need everyone to pay attention here. If it were to go through SN2, I will be able to have a reading from my machine that says it rotated positive 12.5. If it undergo SN1, where it is 50-50, that beaker or the test strip of solution, when I put in the machine, I will read 0. I don't read anything. So yeah, part of it is inverted and part of it stays, but it just is a clear indication that it was SN1 mechanism. Is that clear to everyone? So what happens if I have this chloro-2,2-dimethylpropane? If I look at this structure, can I have one of you quickly tell me, is it a primary, secondary, or tertiary alkyl halide? Primary, because you look at the carbon that is directly bonded to the chloride, the chlorine here. This carbon has 2 hydrogen, it's primary. But come on, look at that one substituent, it's like a tree. It's so bulky that despite that it is only one substituent, it is big enough to repel or block the approach of your nucleophile. This is the effect of steric hindrance that is caused by the bulky groups and prevent a backside attack. I'm missing a 3. Why? Okay? This one is fine because it's too bulky and it presents a steric hindrance. Despite the fact that it's primary, it will still undergo reaction otherwise. Okay, what happened to this one then? How slow is slow? Yeah. How slow is slow? Every class has at least one person that is done with copying this. The physics lecture is very eager to start. Okay, what about this one? This goes back to your tutorial question and Elkin's assignment if I'm not wrong. Because you have a carbocation that has a benzene substituent. That will form this guy. And if you have done your assignment already, you will know the benzene will be able to help with stabilizing the carbocation. Because it is so stabilized. Really, you're trying to copy this diagram? Okay. Carbocation is stabilized by the delocalization of positive charge into the benzene ring. Oh, take a picture, people. Or look at the lecture video online. The chemical test is really quick and really short. Nucleophilic substitution to kick out the halide ion. Add your silver nitrate and you will get PBT. This is something that you have done in your Prac 3, Prac 2. A-round halide does not come out with the ion because your CX bond is super strong. Please refer to your term 1 week for Prac 2. This therefore can be served as a test to distinguish your alkyl halide and A-round halide. The uses are here listed in your notes. Please take note that we have already gone so far. Your organic journey is going to end soon. Chem reps, please collect the next set of lecture notes and tutorial. Thank you so much.